Hi everyone, this is David Ramirez here, and I'll be talking today about buoyant force. Have you ever wondered why you don't sink when you're on a floaty, or why when you're on a cruise ship it never sinks? Well, thankfully, to buoyant force, we were able to keep alive and stay afloat. And yeah, what is buoyant force exactly? Well, buoyant force, the definition of it is the upward force a fluid exerts on an object. It basically is it's Earth's gravity versus the buoyant force. For example, here on the image on the right, we have buoyant force exerting an upward force towards the object of center of mass, and then the weight of the object going downwards. Both both arrows cancel each other out to keep the thing or the object afloat. Look at this as in the normal force and gravitational force on planet Earth acting on us, but in this case on water. Next, the equation. Equation of buoyant force is P, the density. P is the density, which is the density of the fluid or water in most cases. Gravitational acceleration, which is just regular 9.8 meters per second squared. And um, we have the times the volume. Volume is the displacement of the fluid after the object is put on the fluid. Lastly, when we're solving for buoyant force, its unit is measured in newtons. Nextly, also, you may ask yourself, where do we get buoyant force? Where does it all come from? Well, thankfully, thanks to a scientist named Archimedes, his principle, he came up with this. He came up by saying the upward buoyant force that is exerted on an object immersed in a fluid is equal to the weight of the fluid that this body displaces and acts in the upward direction at the center of mass of a displaced fluid. Whew! In other words, what this means is the buoyant force applied by the fluid is equal to the weight of the displacement fluid. Fun fact: Archimedes came with this ideology when he was in a bathtub. He obviously sat down, the water flew up, and that's how buoyant force came to be. Also, um, the if the weight of the water displaced is equal to the weight of the object, it then starts to float. For example, here on the image on the bottom left, I have a block measured in 2 kilograms. It's synced weight in the water, and then obviously the water rises up. The water then goes the water then flows down. The water that was floated down is weighted at 2 kilograms of water, which is also equivalent to the mass of the block. So basically, that's how buoyant force also works. So the water that rises up, the volume, which is this, is also equal to the block. An example of buoyant force of how to calculate. We have what is buoyant force on a 15.5 m square root of 3 wood log that has 50% of its volume submerged in grapeseed oil with a density of 923 kilograms divided by m square root of 3. So we would first, when we start to do this, we would first have to find the volume. Volume is just the percentage, 50%. We'll then convert that to zero point 0.5, and then the number we're given into here, and then we would get 7.75 m to square root of 3. And then after we have that, we already know what P is. G obviously is gravitational and acceleration, which is 9.8. And then we're obviously going to be using the force buoyant equation. Once we have that, we just plug in all the numbers, and then once everything is converted, obviously we will then have to have this in newtons.
All right, team, we're going to be looking at what makes an object float today, and it's going to be a little bit more in depth. So, David taught you about the Archimedes' principle. He also taught you about the buoyancy force. And basically, you know this equation now. You should know it. So let's draw this free body diagram right here. So weight and the buoyancy force. So basically, if you look at this here, the wave force, doesn't this kind of look a little bit like this? Well, negative PGV. Isn't V equal to P over M? So isn't this just negative mg? Well, yes, it is. Now these equations may look similar, but there's a very key difference. So these two equations, can this also just be wrote as this PGV? Well, the difference is these are not talking about the same thing. This wave force is talking about the density and the volume of the object. This is talking about the density and volume of the fluid displaced. So if we think about it, when you submerge an object into fluid, obviously it goes up. You should already know that. But if you think about it, the volume of the fluid displaced will never be different than the volume of the object, than the volume of the submerged object. Because how would it add any sort of how would there be an additional volume? How would more water be displaced when there's less of an object in the water? It's just not true. It's not possible. So basically, the only way for the ball to like go down to start sinking, the only way for that to happen is if the weight force is larger than this force, so it starts accelerating down. Or it doesn't start accelerating down, it goes down, it sinks. So that the only way for that to happen is for the this force to be larger than this force. Well, the only way for this force to be larger than this force is if the weight is if the density is larger, because the volume, like we established earlier, has to stay the same. So only if the density of this object is larger than the density of the liquid is when the object floats or sinks. So you may have heard this before, when an object only floats whenever the density is smaller than the density of the liquid. So you can see here, when the density of the object is larger than this one, this P is larger than the negative P, or okay, that's not a good equation, but when the P of the object is larger than the, or has more magnitude than the P of the displaced liquid, then the wave force is higher, it starts sinking. So yeah, that's pretty much it. And then we can talk about hot air balloons now. So basically, this hot air balloons are a good example of this, as warm air, as you all probably know, rises, and while cool air falls. But why is that? Well, again, it's because the density of the warm air is lower. So the density is lower, it goes up, the cold air falls, it exerts a force on the hot air balloon, and that's what allows it to float. So we're learning about different equations, a couple new equations, fluids, just many different units. So be sure to remember Archimedes' principle and the equations. All right, that's it, team. Uh, Thrasher out.